solutions to our 4.6 notes about using this value of Kw and also the dissociation constant for acids, and how Ricebox can help us in answering questions about, say, weak acids and their pHs. All right, we're going to go through these pretty slowly. The hope is that if anything from this section was a little unclear or you missed a day or two, which I think there was quite a few absences across the board this week, we can hope to fill in some of those gaps for you in as much as we can. All right, so first we want to know what's the concentration of hydroxide in neutral water at 25 degrees Celsius. Okay, so the first big idea is that if you have neutral water, and I actually have these models of water molecules, and we have a bunch of them in, say, a vessel. Okay. Now, very rarely, but every now and then, one of these waters is going to stop being some neutral substance and donate a proton, acting as an acid. It's going to donate one of its protons to another water, a neighboring water. As a result, we still have a lot of waters around, regular old waters, but there is one hydronium made, oops, I was pointing at the hydroxide, an H3O, oxygen, 3 hydrogens, and this would have a positive charge, and an OH, a negative charge. And the whole vessel would have very few hydroniums or hydroxides, but they would in no way be balanced. You'd have one of these guys for every one of these. Now what we got to remember is that this is our acid molecule. It's the thing that makes a substance, a solution, acidic. It's the H3O. And this is our hydronium ion, hydroxide ion, pardon me, as an OH. And it's got a negative charge, and it's what makes a solution basic. And you have an equal mixture of both, and you have a neutral solution, pH of, say, 7. Okay, so we can write that principle chemically with simples. We can say a water mixed with a water sometimes, and the sometimes means it's going to live in equilibrium. It's going to form one hydronium, H3O plus, that was this guy, and one hydroxide ion, which is this guy, from 2 water molecules. And these live in equilibrium. So as much as water molecules are colliding and exchanging a proton and turning into these guys, as much as that happens, for every 2 waters that collide and form a hydronium and a hydroxide, some hydroxides floating around meets a hydronium, steals a proton back, and then they form regular waters again. And the rate of the forward reaction is equal to the rate of the reverse reaction because it's in equilibrium. Okay. So if this is in equilibrium, and I should probably mention these are liquid waters, whereas we would call this aqueous, floating in water, aqueous. And we know that this could be expressed in terms of an equilibrium constant. And an equilibrium constant refers to the concentration of products divided by the concentration of reactants. Okay. So I would say, okay, the KEQ of products here is it's going to be H3O plus. That's one of my products, and I multiply that by my hydroxide, which is another one of my products. And my reactants are actually both liquids. So they actually don't show up. We don't say that there's a concentration of liquid. You might say there's a density of liquid, same with solids, but they don't end up in our KEQ expression. Okay. Now, this reaction has a particular name. I should call this KEQ W. It's the constant for the dissociation of water. And if we look on our table, we notice that this describes aqueous solutions at room temperature, meaning for our purposes 25 degrees Celsius. And so chemists often imagine very warm rooms where they're about 25 degrees. And that seems to be a very typical temperature for a lot of the things we deal with in chemistry. All right, and if I look all the way down, water is a pretty weak acid. It can act as an acid sometimes, as we saw that it would when it would donate a proton to something else, in this case another water. So water can act as an acid, but it's very weak. And if we look down from our strong acids all the way down to our weak acids, you might notice, oh, water is at the very bottom, right before we get to these, by definition, not acidic things. And water, here we go, it makes this hydronium ion, which is often abbreviated H+ on our chart, and a hydroxide ion. And the equilibrium constant, which is left labeled in this right column, is 1 times 10 to the negative 14. So if this question wants to know what is the concentration of hydroxide in neutral water, well, I know that at 25 degrees Celsius, this Kw at 25 degrees Celsius is 1 times 10 to the negative 14. And that is equal to the concentration of hydronium plus the concentration of hydroxide. The question is, well, how big is the concentration of hydroxide? That's what we're asked for. Okay. Now, in order to do that, I have to recognize a pretty important principle. And that principle is that when this reaction occurs and there's a proton donation by some water to another water, you always are going to get an equal number of both. However many, you can't have more hydroniums in this case than you can hydroxides, because it's neutral water, first of all, and more importantly, it's only made from other water molecules. So every time a water molecule loses a proton, you get one hydronium and one hydroxide. So whatever the concentration is of hydroxide, it's going to be equal to the concentration of hydronium. So I can sum that up by saying that maybe I don't know the concentration of hydroxide or hydronium or hydroxide, but I can label them X. So I know the concentration of hydroxide is equal to the concentration of hydronium when a solution is neutral. So I can say then that I have 1 times 10 to the negative 14, and that's equal to x squared. Now, if I actually want to find out what x is, I can square root. Undo squaring. That's going to give me my x value, which is the square root of 10 to the negative 14. So I'll do the square root of 10 to the negative 14. I'm actually not including the 1 times 10 to the negative 14 because it doesn't really matter that I'm multiplying by 1. And when I do that, I get 0.00000001, or 1 times 10 to the negative 7 moles for every liter. And so what that tells us is that, well, what did X stand for? X stood for the hydroxide concentration. It tells us the hydroxide concentration is 1 times 10 to the negative 7 moles for every liter. And that's what we were looking for. It also happens to be the hydronium concentration. And what's interesting is if we take the negative logarithm of this and we find the pOH of this, we get, I took the positive logarithm. Silly me, a negative logarithm of 0.000001 0.0000001, and we get 7. So the pH of this is 7. Pardon me, the POH. That means we have a POH 7, which means we also have a pH of 7, which is what we know about neutral water. The pH is 7, POH is 7. Okay. Great. Okay, let's move on to the next question. If the hydronium ion concentration in a can of Coca-Cola is 3.56 times 10 to the negative 6 moles for every liter, what's the hydronium concentration at 25 degrees Celsius? Okay, so one thing that's really important is at 25 degrees Celsius, no matter what, we always know that 1 times 10 to the negative 14 is equal to the concentration of hydronium ions times the concentration of hydroxide ions. And that's a general principle that we need for this question. Now, in this question, we know the hydronium ion concentration is given. It's 3.56 times 10 to the negative 6 moles for every liter. So I can say in this example of Coca-Cola, we get 3.56 times 10 to the negative 6 moles for every liter. That's times the hydroxide concentration. Now, if I want to isolate my hydroxide concentration, I'm just going to divide both sides by 3.56 times 10 to the negative 6 moles for every liter. Now, actually, the units kind of get funky. Remember, with our equilibrium constants, always, we get some sort of funky unit here. So actually, it probably wasn't the best idea for me to include the units. It's just a force of habit. And as a result, where'd my red pen go? There it is. You guys cancel out. And I divide this side by 3.56 times 10 to the negative 6 as well. I got, I'll take e to the negative 14, 10 to the negative 14. I'm going to divide it by 3.56 times 10 to the negative 6. And we're going to get 0.000000002. I actually kind of like scientific notation. I feel like I'm rounding something off of there. So if you express that answer, that's actually fine. However, I think I'm going to change the setting of my calculator if I know how, which I may not. Divided by zounds. Okay. 3. Let's try exponents. No. All right. Well, fine. I guess I'll just have to deal with that. Oh, here we go. Sorry, guys. You can scrub through this as I'm playing with the calculator. And, all right, so let's go mode. No, I don't want to clear. I want to mode. How do I access that color? It's ridiculous. Ah! Here we go. Okay. 0. Perfect. Okay, I'm just going to try the calculation again. Now with scientific notation. Exponent, negative 14, divided by 3.56 times 10 to the negative 6. I get 2.8. I did, and it did round really poorly, actually. 2.8 times 10 to the negative 9. And that's equal to the hydroxide concentration. And that would be in moles for every liter. Okay, now if you would like to know how to get your calculator to not express a long string of decimals, but rather express everything in scientific notation, you can let me know, and we can work that out. Flex is a good time to do something like that. Yeah. All right. So let's take a stab at some of these more meaty questions. Question 3 here. All right. So question 3 asks, what is the hydronium ion concentration of a 0.15 molar acetic acid solution? Okay, so I know that when I put acetic acid in water, it's an acid, so it is going to react. It's going to donate a proton. That's what acids do. Here's my acetic acid here. Acetic acid. So it donates a proton to a water molecule and makes a hydronium ion, which is, again, condensed on this sheet. It just reflects a proton. But of course, a proton itself isn't just floating around in solution. It's always attached. And some acetate. Okay. So I can think about a solution here. And this is mostly waters. And so I'm going to draw some waters in. All right, I don't want to get it too cluttered. And I can imagine this isn't a very concentrated solution, so I might draw maybe 3 CH3COOs. CH3COOH. I should probably draw maybe 4, so CH3COOH. 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 I'll draw one more up here. All right. Now, what happens in this solution is that, now we saw when we looked on our table of acids and bases that our acetic acid is not a strong acid. So it does not dissociate completely with one of these unidirectional arrows, where every single one of these turns into one of these. Every single reactant turns into a product. But in fact, it is in equilibrium. And we know about weak acids that very few of them dissociate. That's a very key idea. So maybe 1 out of the 5 I've drawn here is going to donate a proton to a water. And so as a result, we have this solution in which we still have mostly acetic acids. However, we have this one new molecule called an acetate. Well, I should probably draw my waters. All the waters that are still waters, which is most of them. H2O, 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 H2O. But we get this new acid molecule, the H3O, the hydronium ion. And we also get this one acetate ion, which I'm going to draw in green, which is CH3COO minus. That's pretty rare. Most of them don't react, but every now and then one does. I've actually overrepresented how many of them would react. In fact, you'd probably need more like 100 acetic acids before one of them deprotonated, rather than 1 in 5. So it's a little misleading what I've drawn here. It implies that the ratio is a little high for deprotonation, because a weak acid, we talked about less than 5%. To be a weak acid, less than 5% deprotonation. Protonation? How do I spell protonation? Spelling? Let me make a little note. I actually forget how to spell deprotonation. Apologize. And that's a less than symbol. So less than 5% will deprotonate. So maybe if you have 100, at less than 5 of them would react. And so if you have 20, maybe 1 or even none would deprotonate or lose a proton, donate a proton. All right, so now we have a picture of what's going on here. I know I have a concentration of 0.15 molar CH3COOH. That means if there's a liter in here, there's 0.15 moles of acetic acid, a root, or like you can think about it originally. And then at equilibrium, you have some number of these guys and some number of those guys, but mostly acetic acids. All right, great. So what we can do is we can sum up this reaction. We can say CH3COOH plus a water, which is in a liquid. This is an aqueous form, floating around in solutions. These live in equilibrium with the protonated form of water, which is a hydronium ion, which is aqueous, and some acetate, this negatively charged ion, also known as an anion. That's also aqueous. And I want to know what is the concentration of these guys? That's what I'm looking for. What is the concentration of H3O plus? Question mark. How do we find that out? Well, it turns out people have worked with acetic acid a lot, and they have looked at it in different concentrations of solutions and found that there's this general pattern that there is a ratio of how many products are made for every amount of reactants you add or have. And that's called equilibrium constant. And so we know, if we look on our table for acetic acid, that the ratio of products divided by reactants is 1.8 times 10 to the negative 5, which is small. It's like, I'm not sure, like 1 in 10,000 for every amount of products. You have like 1 in 10,000 of a product for the number of reactants you have. The number of reactants you have is, say, something like 10,000 times more reactants than products. We have many more of the reactants than we have products. Now, the way we talk about how much we add, which we think of as an initial condition, and how much we have of protonated water or hydronium, we think of that being an equilibrium condition. And when we're comparing initial and equilibrium values, we need a rice box to do that. So I've already written our reaction here, and we're going to think of initial, change, and equilibrium reactions. All right. Now, I know that initially I can think of there being 0.15 moles for every liter of acetic acid. And I know that in this initial case, before equilibrium has occurred, you say there are none of these hydronium ions and no acetates. And then we're going to change, but we're not sure how much. We're not sure how much of the acetic acids we're going to lose or how many protons we're going to gain. So I'm just going to represent that as a minus x. We're going to lose some number of moles for every liter of these guys. We're going to gain some number of moles for every liter of each of these characters. And so that means at equilibrium we'll have 0.15 minus x acetic acids. We'll have 0 plus x, or x, hydronium ions, and 0 plus x, or x, acetates. And I can say, I can find my equilibrium constant for this, which I call Ka, not Keq, just because we're talking about an acid here. And that'll tell us that our hydronium ion concentration times our acetate concentration, the concentration of our products over our reactants, divided by the acetic acid concentration, is going to be equal to our Ka. Now, we looked up our Ka earlier. It was 1.8 times 10 to the negative 5. So I could say 1.8 times 10 to the negative 5 is equal to the concentration of hydronium, which is x, times the concentration of acetic acid, which is x, which I'm going to write as x squared, over 0.15 minus x. Okay. Now, this is a situation where we have to make a simplifying assumption. If we don't, we've got a power of x to the power of 1 and x to the power of 2 here, and we're only going to be able to solve that using the quadratic formula, or some really fancy grade 11 quadratics math, called completing the square, which would be pretty funky with the numbers we have, and impressive if you could do it. So instead, we're going to make a simplifying assumption. We're going to say, assume that 0.15 minus x is approximately equal to 0.15. What that means is that the concentration of this stuff we had initially is approximately equal to 0.15 molar CH3COOH in here. That however many we lost is so small that when we take away that number of acetic acids for every liter, it's going to be so minuscule that it's not really going to affect the value of this number much at all. And so if we make that assumption, then we get to rewrite this equation. We get to say 1.8 times 10 to the negative 5 is equal to x squared over 0.15, which is much more trivial to solve. We're just going to isolate x by multiplying both sides by 0.15. And we'll cancel those guys out. We get x squared is equal to 0.15 times 1.8 to the power of negative 5. You get 2.7 times 10 to the negative 6. And then we'll isolate x by square rooting both sides. We're going to get x is equal to the square root of this number, which is going to be 1.64 times 10 to the negative 3. And okay, that's fine. Now, what was x anyway? Well, it's important whenever we're done, we're like, okay, we found x, but that might not be our answer. That might not have been what we were looking for. It might just help us find what we were looking for. So we go back to the rice box and we say, okay, x was introduced to represent the equilibrium concentration of hydronium ions, which is what we were looking for in the first place. So it looks like this value is x is our answer in this case. It's not just something we didn't know. So that means a concentration of hydronium ions is equal to 1.64 times 10 to the negative 3 moles for every liter. Okay. Now, so question 4 asks, what's the pH of a 0.15 molar CH3COOH solution? Okay, well, need some more paper. Okay, so we could start this from base principles if we wanted to. However, we know the hydronium ion concentration of a 0.15 molar acetic acid solution. So from question 3, we can say the hydronium ion concentration is equal to 1.64 times 10 to the negative 3 moles for every liter. Okay, so in that case, if we're looking for the pH, well, we know the pH and the hydronium ion concentration are related, as one is the negative logarithm of the other. So we take that value and we plug it in, plug a chug, we say pH is equal to the negative log of 1.64 times 10 to the negative 3, and see what happens. So we get the negative logarithm, 1.64 times 10 to the power of negative 3. And this is a situation where, because my calculator is in scientific notation, I get this number times 10 to the power of 0. And 10 to the power of 0 is 1. Every number to the power of 0 is 1. So actually, this is just a funny way of saying 2.78, which I'm going to call 2.8. So pH is equal to 2.8. Okay. And we get to do a similar sort of move with question 5, because we're asked for the pOH. So we get to say from question 4, we know that the pH equals 2.8. And we know that to find the pOH, we know pOH plus pH is always equal to 14. Well, it's not actually always equal to 14. It is at 25 degrees Celsius. But I have suggested to you guys that if I forget to write negative 25 degrees Celsius, which I did in this case, you need to assume we're talking 25 degrees Celsius. And you can worry about the weird cases later if you choose to pursue chemistry. And maybe in first year or second year, you might deal with varying the temperature and all the different consequences that come to that with that. Okay, so if I know my pH is 2.8, I'll just plug it in and then solve for pOH by subtracting 2.8 from both sides. And so it says that pOH is equal to 14 minus 2.8. And that's, okay, so now is where the mode is actually really kind of a hindrance more than a help. I'm pretty comfortable with this, but you might not be actually. 1.12 times 10 to the 1. Well, I think I'll just turn this into a normal form for now. Okay, so that means it's 11.2. You might not have even needed a calculator for that. Okay. Okay. So let's move on. So in the next question, we're asked for the pH of a 3 times 10 to the negative 3 molar benzoic acid solution. So that's kind of bringing it, the questions of 3 and 4 together. So if you're kind of confused about what's going on to begin with, I would really consider or suggest you go back and look at the part of the video where we talk about how to do question 3. But I think, okay, so let's see, what do we know? We know the concentration of benzoic acid. Oh, man, I don't know what benzoic acid is off the top of my head. Oh, wait. No, wait, yeah, benzene? Benzoic acid. Okay, yeah, so it's a benzene ring with an organic acid attached to it. Okay, C6H5COOH. We know that's equal to 3.00 times 10 to the negative 3 moles for every liter. Okay. And we need to know the pH. Now, we saw before, if we knew the concentration of a weak acid, we could find the hydronium ion concentration using our Ka. So maybe if we use our Ka to find our hydronium ion concentration, we can find the pH by using a negative logarithm of our hydronium ion concentration. Okay, so let's give that a try. So our first step in the last question was to write a reaction. So we have a benzoic acid solution, which means it's mixed with water, liquid water. And we know that it's an acid, which means it donates a proton to water. Okay. And that it lives in equilibrium. When it does is it makes a hydronium ion. And I can imagine what this thing would look like if it lost that hydrogen. It's going to have all these small atoms, and it's going to have a negative charge. If I wasn't comfortable with that, I could just look on my sheet and see the products after benzoic acid donates a proton. CH3COO. That's aqueous. Okay. And we said we'll make a rice box. Okay. So we know the concentration of the acid. It's 3.00 times 10 to the negative 3 moles for every liter. And we know water we don't really express water in terms of concentration. We would definitely start with 0 of our acid, and then we would add some amount, really similar to what we did in question 3. And then we get 3.00 times 10 to the negative 3 minus x. and we just have x and x here. And you will probably find that as you do enough of these, you recognize some patterns here. So I'm going to express the concentration of the reactants over the products here. Set that backwards. Products over the reactants. 0.00 times 10 to the negative 3 minus x. And, sorry, I'm just thinking about something. Okay, so we'll make an assumption here. We'll assume that 3.00 times 10 to the negative 3 minus x is approximately equal to 3.00 times 10 to the negative 3. They're relatively similar, and this time we're really going to make an effort to come back and check. So that means we can rewrite this as Ka, which is x squared over 3.00 times 10 to the negative 3. And I know our Ka. It's on our chart here. Benzoic acid, so 6.5 times 10 to the negative 5. So we get 6.5 times 10 to the negative 5 is equal to x squared over 3.00 times 10 to the negative 3. Well, we'll multiply both sides by 3.00 times 10 to the negative 3. And that will cancel these guys out entirely. So we'll just have x squared is equal to, that's a 3. 3 times 10 to the negative 3 times 6.5 10 to the negative 5. So we get 1.95 times 10 to the negative 7 is equal to x squared. And we're going to square root both sides. And we get 4.41 times 10 to the negative 4 moles for every liter is equal to x. Now, okay, so we're going to leave it there for now. All right, so what is x? That's our hydronium ion concentration. So now we can find our hydronium ion. We know our hydronium ion concentration is our hydronium ion concentration is 4.41 times 10 to the negative 4 moles for every liter. And if I want to find our pH, then we're going to use a negative logarithm. So pH is equal to negative logarithm of 4.41 times 10 to the negative 4 moles for every liter. So our pH is equal to the negative log of this answer. And we get 3.35. So that's our pH of the solution. Okay, last question. What is the pH of a 4.5 times 10 to the negative 5 molar citric acid solution? So you're going to find actually the math is pretty much identical to question 6. So I'm actually going to run through this really quickly. Just to have a complete solution set. So if you are not sure about any of these stages, I would suggest going back to the question 6 and making sure you really understood everything in that step. And if there's still something about this one that's funky, let me know and we can try to work through it. So first thing I'm going to do is write this reaction. I got a hydronium ion as a result and some weird citrate ion. Okay, and we'll make a rice box for this. pH, pardon me, the initial concentration is 4.5 times 10 to the negative 5. And we'll lose x, so we'll get 4.5 times 10 to the negative 5 minus x. 0, 0. We'll add x, and we get x and x. So that means our Ka, which in this case is 7.1 times 10 to the negative 4, is equal to x squared over 4.5 times 10 to the negative 5 minus x. Okay, so we're going to assume that 4.5 times 10 to the negative 5 minus x is approximately equal to 4.5 times 10 to the negative 5. And if we can assume that, because it's a weak acid, then we get 7.1 times 10 to the negative 4 is equal to x squared over 4.5 times 10 to the negative 5. And I'm going to multiply both sides by 4.5 times 10 to the negative 5. And cancel this guy out. Times 7.1 times 10 to the negative 4. And we get 3.195. Or 3.195 times 10 to the negative 8 is equal to x squared. We're going to square root that. And we get 1.79 times 10 to the negative 4 is equal to x. And so that means the hydronium ion concentration is equal to 1.79 times 10 to the negative 4 molar. And so to find the pH, that's going to be equal to the negative logarithm of 1.79 times 10 to the negative 4. Negative logarithm of 1.79 times 10 to the negative 4. So pH is equal to 3.7. All right. So I went through that last example pretty quick. Let me know if you had any troubles with any of those, and we can talk about it next week. Otherwise, enjoy your weekend.